Welcome back as we explore further down the kinetics unit and or reaction rate unit. We're now going to begin to explore reactant concentration and time. So how does the concentration of the reactant or reactants and time relate? So knowing the concentration over time is more practical. We can use calculus to develop the relationship between concentration versus time. So calculus will have been used and we can get to this algebraic relationship between concentration and time. This is for a first order reaction or reactants. Okay, a first order reaction or reactants. So let's talk about what all these pieces mean. This is the concentration, original concentration on top over the final concentration. I also think of it as the now, N-O-W, almost looks like a zero, the now and the later. The now concentration and the later concentration. This is your reaction rate constant, and this is your time. Okay, so here this is just isolating what these different things mean as I went over this a moment ago. I do want to point out that sometimes you will see me write the not. This means the initial concentration with the little zero on the outside of the square brackets. Doesn't matter if it's on the inside or the outside. When it has this zero or not symbol, it means it's initial or beginning. Okay, so for example, 10. If it's not stated, then we're going to assume something is first order. This is not the type that we've done before. We have to be told, or we'll have to calculate with a graph, which we'll learn in just a moment. Calculate with a graph is probably not the correct phrase to use there, but we will have to determine with a graph, or three graphs, these three graphs. So what you see here is a formula page. You will get the use of this on a test or a quiz, any kind of assessment. We're going to need to, sometimes we will need to plot, make the plot of concentration versus time, the natural log of concentration versus time, and the inverse of concentration versus time, and then which one of these three graphs makes the most linear plot. That's the order the reaction is. So not calculating, not being told that way. So sometimes we'll be told, sometimes we won't. How do you know when you need to use a graph determinant? You'll have a data table that'll have concentration and time in it, or a table that can be created from concentration versus time. So this doesn't have a table where we can calculate or plot anything. We don't have concentration times, a list of them enough to plot something. So because it doesn't tell us, we're going to assume it to be first order, and then we will begin from there. So if it's first order, then that means that we're going to be using this line of our formula page. Okay, and any of these things are fair game for a calculation. You're going to see that we're going to be mostly reside in this area for the most part. Okay, in this concentration time relationship or the integrated rate law column. I also think it's helpful to point out what we have. Here we have T, time, and we have initial concentration says starting, so this is my now concentration. And I also think it's important to point out that we have K. It's labeled up here, but just to highlight it. So we have a few pieces. Let's see what we're solving for. It says to calculate for A, we're doing this is just part A, the concentration. So the later concentration, we're given the now, beginning, the initial. We want to know what's the concentration later. So we're looking for concentration. So we don't have a rate, so we can't use this column. That's not going to help us. We don't have a graph, and we don't even have concentration in here. This is helpful, possibility, because we have concentration. This doesn't have a place to plug in concentration or time, and this is only for graphing. So we're using this, as I said, that'll be used the most often. So that'll be the formula that we will use. So here we have the integrated rate law. The ln of the initial concentration over the final concentration equals K times T. Remember, this is our rate constant. So we're going to plug in our initial concentration here. I got that from right there. We know K already was given, and we know it lasted for 6 minutes. It's very important, especially in your homework, that you're very careful with the K and the T. If your units of T are not the same units of time in your K, let me say that again, listen carefully. If your units of time do not have the same unit of time that is represented in the K, convert your unit of time into whatever unit. So if this would have been minutes and seconds, I would first convert this into, if this would have been minute and seconds, I want to make sure I said that right, I would first convert my time into seconds before I plugged it in. So convert your time so that it has the same unit of time as your K has. This one happens to have the same unit, so we're good to go. So we're going to multiply these. And before we do that, we know that we have, I like to say we have an unknown trapped inside an ln. We have an unknown trapped inside an ln, so we're going to ex both sides. Take the e of both sides, so thinking back to your algebra class or maybe pre-calculus, I'm not sure where you guys do this. So when I e both sides, right, so this is e, and then this is just 2.1 is this times this, right? So I e both sides. What happens when I e an ln, it's like I erase the e and the ln, and this just drops down. And then this is a numeric value because I punched this onto my calculator. So it should be the second function of your ln button. So look at your calculators and find the ex button, or the second function of your ln button. So when I e an ln, it just drops down. When I e the 2.1, I got 8.17. So now we're going to go over here and solve for our concentration. Remember, that's what we were solving for. So I put 8.17 over 1. For some reason, that seems to help my students when I say that. We're going to cross multiply to get a isolated, or so it's easier to deal with. So now we have, and we're going to continue on isolating a, or getting a by itself. So we know when we cross multiply, we'd get this. And now I'm going to divide both sides by 8.17, and I get a concentration of 0.02448 molar.